All right, the next unit is on Chapter 4, and Chapter 4 is dealing with chemical reactions that occur in aqueous solutions, so water-based solutions. Now, one of the first things that you're expected to memorize for the national exam is a solubility rule. If you remember back from honors chemistry, on Blue Chem Helper, there was a listing of a table that allowed you to determine if a substance was soluble in water or not. For the national exam, they expect you to memorize this one solubility rule. Any chemical compound that contains nitrate, so aluminum nitrate, silver nitrate, copper nitrate, any nitrate compound is soluble in water. Any ammonium compound, remember ammonium, NH4+, is the only positive polyatomic ion that you have to be concerned with for the AP Chemistry exam. Any ammonium compound, when placed in water, is soluble. And lastly, any group 1 compound, metal compound, is soluble in water. So group 1 would be sodium, potassium, rubidium, cesium, moving down. So any chemical compound containing a metal in group 1, the start of the compound is a group 1 metal. That substance is also soluble in water. Now the focus of this chapter is going to be on a couple different things. First of all, we're going to look at net ionic equations. And the first two lectures for this week is going to look at net ionic equations, one for precipitation reactions and one for acid-base reactions. So a net ionic equation is what the national exam wants your final equation to be if they ask you to submit it. Usually in chemistry and honors, you are asked to give a molecular equation. In this unit, we want to only put down the species, the particles that are involved in the actual chemistry of the chemical reaction. Anything that's not is called a spectator ion, is not part of the net ionic equation. And I'll show you how that goes in this lecture. Okay? And lastly, stoichiometry. Now we're going to look at stoichiometry. Instead of mass stoichiometry, we're now going to look at solution stoichiometry. So now we're going to look at concepts of molarity and how we can use molarity to figure out the moles of the reacting substances and then figure out the products. All right, to begin precipitation reactions, we have to first understand how ionic compounds dissociate in water. The key word there is dissociate. When you have an ionic compound that is soluble in water, so if it's soluble in water, it is going to dissociate. Dissociate means the ions that are present. Remember, in an ionic compound, the positive and negative ions are attracted to each other in something called an ionic bond. In order for that ionic bond to break apart and we form ions into water, we must have enough attraction of the ions to the water molecules that will cause it to be energetically favorable. And when that happens, if you have a soluble substance, the affinity towards the water molecule is greater than the affinity to the ions to themselves. And therefore, the water causes the particle to break apart, and now in the solution we have suspended ions. So if I put sodium carbonate into water, now I'm going to put water over the arrow. This just tells me the medium that I'm going to put this in. If I put sodium carbonate into water, if I look at my solubility rule, you'll notice that sodium is a group 1 ion, and therefore we will know for the national exam that this compound is soluble in water. So when it dissociates, it's going to break apart into sodium ions, and group 1 ions are always monatomic. It's sodium plus 1. Group 1s have a plus 1 charge. Plus carbonate, which has got a -2 charge to it. Carbonate ions, -2. Again, from the first unit, you should have good understanding of the ions. If you don't, obviously you have the ability to use your phone or other resources to look up the charges on these. So carbonate has a charge of -2. Now, theoretically, because these are soluble, the state of matter would be aqueous, because they're soluble in water. But we do not put aqueous down, because if it's an ion, for the sake of this national exam, we know that if it's an ion, it's an aqueous or a soluble ion in water, okay? Which I'll show you for the next one. Now, am I balanced here? No, you'll notice that the reason why there's 2 sodiums there is to balance. The sodium ions have a +1 charge, the carbonate's -2, so we need 2 of them. So this is the biggest mistake students make. They see this 2 here, and when they dissociate it, they want to dissociate it like this, where they show the ions, where they simply break the 2 apart from each other. This is not correct. You have to identify the state of the ions, and then if there's more than one of them, we put that now as a subscript. Now it gets converted into a coefficient. So there's 2 sodium ions for every carbonate ion. So if I were to draw a picture of this in a beaker, and I wanted to draw a proper representation for every sodium carbonate particle that dissolves. So if I put some sodium carbonate here into water, as it dissolves, what I'm going to get is I'm going to get 2 sodium ions for every carbonate ions. So in solution form, I'm going to have twice as many sodium ions as carbonate ions. And that has to be the case because if I add up all the charges, that has to add up to 0. The overall number of charge has to stay constant in the solution because the ionic compound is not charged to begin with. So the charges of the ions should always summate to 0 in these pictorial examples of these ions. All right, go ahead now if you want to pause the lecture and go ahead and do calcium chloride and see if you get the right ions. Okay, so if you're completed now, if I put calcium chloride into water, we get a calcium ion and 2 chloride ions. Now, you might say, well, Mr. K, calcium and chlorine, that isn't a group 1, it's not ammonium, it's nitrate. You're correct. What they'd have to tell you on the national exam is that calcium chloride forms a solution. If you see the word solution, that immediately implies that that substance is soluble in water. So look for verbiage like that to indicate if it is soluble or not. If they don't say that, if they didn't tell you that calcium chloride isn't soluble in water, then based on our solubility rule, you would predict that it's actually a precipitate. But if you see the word solutions, you should then know that it is soluble and therefore should break apart into ions. So this breaking apart ions is called dissociation. Now, whenever we form ions in solution, if something forms ions in solution, this is said to be an electrolyte. Your online homework on Pearson is going to focus a lot on that. Electrolytes are chemical compounds that make water conductive to carry electrical current, and that's because there's ions present in solution. And when I put electrical current into the material, the ions migrate throughout the solution, and that migration of ions is in essence conducting electrical current. So with that, any substance that forms ions in solution is called an electrolyte. Okay? Gatorade has made billions and billions of dollars on this advertising of this idea of electrolytes. It simply means that when we sweat, we release or lose sodium and potassium ions as we sweat. That's why sweat tastes salty. If we don't replace those ions, then we are going to have an electrical imbalance, and that's what causes cramping. Okay? All right, now what happens when we mix these 2 solutions together? If I mix sodium carbonate with calcium chloride together, now I'm going to do the molecular equation. So this is typically all the reactions we're going to focus here on this first unit are going to be double replacement reactions. So the sodium and the calcium ions are going to switch positions, and we're going to form the compound calcium carbonate and sodium chloride. Oops, I did that wrong. Okay, calcium has got +2 ions and carbonate's -2, so they come together in a 1-to-1 ratio. Sodium is +1 and the halogens, chloride, are always -1. They too form a 1-to-1 ratio. Now the next step is after we get the right formulas, the key question becomes balancing. You'll notice that there's 2 sodium and 2 chlorines, so to balance it I need 2 sodium chlorides. Lastly, states of matter. Now this is where we need to know our solubility rule. If I look at calcium carbonate, if you look at the solubility rule, would you predict calcium carbonate to be soluble or insoluble? Since it doesn't contain a nitrate, it doesn't contain ammonium, and it doesn't contain a group 1, calcium is group 2, we would predict that calcium carbonate is a solid. It does not stay soluble in water. Therefore, it is a precipitate. A precipitate is an ionic compound that is not soluble in water, and therefore it precipitates out of the solution. Sodium chloride contains Na, group 1. Because it contains group 1, it's soluble in water. So this is an example of a molecular equation that we might have had in honors chemistry, in which now we're able to properly predict all of the states of matter of the reactants and the products. Again, if the reactants, they tell you that they're solutions, then we automatically assume that they're aqueous substances. Okay? All right, real quickly here, finish the table below. Identify with the following 4 chemicals. Based on the solubility rule, would you predict that these are soluble in water or insoluble in water? Go ahead and try. Okay, the first one, nickel nitrate. You see nitrate. If something contains a nitrate, it is soluble in water. Therefore, it would be aqueous in water. It would be soluble in water. It's an electrolyte, produces ions in solution. Barium chloride doesn't contain group 1, doesn't contain ammonium, doesn't contain nitrate. We would predict this is insoluble in water. It would have an S after it, and because it's insoluble in water, it does not produce ions in water, and therefore is a non-electrolyte. It's not electrolyte. It doesn't produce ions in solution. Lead 2 sulfate. Again, no nitrates, no ammoniums, no group 1s. Based on the solubility rule, we would predict insoluble. And the same thing for iron chloride. Now, in actuality, lead 2 sulfate actually is soluble in water, but based on our solubility rule, we would have to be told that it's a solution to begin with. If they do not tell you that, the proper prediction is insoluble because it doesn't contain a group 1, a nitrate, or ammonium. All right? So, if they say solution, then that tells you that it is soluble in water. Okay? All right. So, now if I look at that reaction of calcium carbonate, let's back it up a little bit here. Sodium carbonate plus calcium chloride This is called the molecular balanced equation. This is what we had in honors chemistry. Now, at the end of the year, we started doing some of these net ionic equations, but again, some people were very good and diligent and did it, others of you were not. So this might be new for you, some of you, this might be review. Anything that is aqueous is soluble in water, and therefore it dissociates into water as long as it's an ionic compound. If it contains a metal and a nonmetal or a polyatomic ion, if it's aqueous, it's going to separate into its ions, and that's what I'm going to do. Anything labeled with an aqueous substance, I'm going to separate. Anything that's a solid, liquid, or gas, I'm going to leave, and I'm not going to dissociate it. So, 2 sodium ions plus a carbonate ion, and again, because they're ions, I don't have to keep putting AQ after them. You can, but you don't have to. A calcium ion and 2 chloride ions. Okay? Mix together, and we form the insoluble calcium carbonate, which because of the solid, it stays together. Sodium chloride is aqueous, it separates, and now there is a 2 in front of it. Because there's a 2 in front of it, it's like multiplicative. We apply that there's 2 sodium ions, and there's 2 chloride ions to keep the reaction balanced and to keep the charge in the solution neutral. Again, keyword there, neutrality in the solution. Just many positives as negatives. This right here is called the net complete ionic equation. This is not what they want on a national exam. What they want you now to identify is, are there any spectator ions? Are there any ions the same on the left side of the reaction as there is on the right side? And when we look here, you'll notice that there's 2 sodium ions on the right. There are also 2 sodium ions on the left. Nothing chemically has changed with the sodium ions, and therefore they're a spectator ion, and I cross them off. The same thing is true for the chloride ions. The carbonate and calcium you do not see as ions in solution. Instead, they've come together to form a precipitate. And therefore, calcium ions plus carbonate ions produces calcium carbonate. This is your first example of a net ionic reaction. That's a precipitation reaction. I always abbreviate precipitation as PPT. This is an example of a net ionic precipitation reaction. It only shows the ions involved in the chemical change, what causes the chemical reaction. The sodium ions and the chloride ions, these are called spectator ions. Just like your parents might be spectating you when you're playing an athletic event or in some other type of competition or in a musical event or a drama club. They're spectating. So sodium ions and chloride ions stay in the solution the entire time. They do not change chemically at all. They were there before the solution, they're there after the solution, and therefore they are spectator ions. Because of the solubility rule at the top, nitrates, ammoniums, and group 1s are always going to be spectator ions in aqueous solutions because they will not form precipitates. They're going to always be soluble in water. So those are examples of spectator ions. Okay? All right, let's turn to the next. All right, so now let's go ahead and do another example. So what I'd like you to do real quickly is to pause the lecture and go ahead and try to do letter B. Try to, first of all, complete the molecular equation, then break it apart into the complete ionic equation, and then at the very end, supply the net ionic equation and see if you get the same answer as I do. Now, I'm going to tell you ahead of time, these are both solutions. And because you see the word solution, even though they might not follow the solubility rule, I'm telling you that if you were to look them up online, you'd find out that these chemical compounds are indeed solutions and they're soluble in water. Okay? And that'd be the case for all 4 of these. All 4 of these, the reactants are aqueous because they're all solutions to begin with. Now, on the product side, use your solubility rule to predict if it's soluble or insoluble. All right, go ahead, try to do letter B, and we'll see if you get it right. Okay, so again, these are double replacement reactions. So the sodium is going to go with the nitrate. Sodium is +1, nitrate's -1. So they come together in a 1-to-1 ratio. Plus copper on this side, nitrate's -1. Since there's 2 of them, the total charge in the copper nitrate is -2. So the copper has to be +2. Remember, elements in the D block might have more than one oxidation or charge state. You have to use the identification of the negative ion to figure out the charge of the D block metals. In this case, it's copper 2. Whenever we have a double replacement reaction, the charge on the metal ion on the left side, the reactant side, is still the same on the right side. Hydroxide is a polyatomic ion. It's OH with a -1 charge. Whenever the ions do not balance, we cross-drop, and what's left over is the new chemical formula, a 1-to-2 ratio for copper 2 hydroxide. I'm going to grab my eraser now, and I am going to erase all of these charges because they no longer should be present. And now I'm going to look at my solubility rule. Sodium nitrate contains group 1 and a nitrate, so that's going to be aqueous. Copper 2 hydroxide does not contain a group 1, doesn't contain nitrates or ammonium, and therefore we predict it to be insoluble, okay, and therefore form a precipitate. Am I balanced? Well, no. You'll see there's 2 nitrates on the left, so I need to put a 2 on the right. That gives me 2 sodium, so I got to come over here and put a 2 in front of the sodium hydroxide, and now I'm balanced. So 2 sodium hydroxides, 1 copper nitrate, 2 sodium nitrates, and 1 copper hydroxide. There is the complete balanced equation. Technically, both of these would be aqueous, and that's the molecular equation. If I ask for the net ionic, which I will for the homework, the next step now is to break apart anything that's aqueous. The copper hydroxide will not be broken apart because it's a solid. So now there's a 2 in front of the sodium hydroxide, so that's 2 sodium ions, 2 hydroxide ions, plus a copper +2 ion. There's only one of them. It's got a charge of +2. The nitrate has a subscript, so it becomes now a coefficient. 2 sodium ions, 2 nitrate ions, and the solid stays together as a precipitate. All right, now before you move on, you should always check the charge. If I look on the left side before the arrow, there's 2 sodium ions +2, 2 hydroxides -2, that cancels out. a +2 copper, and 2 -1s, nitrates cancel. So the whole charge on the left side is 0. On the right side, 2 sodium ions, 2 nitrate ions cancel, and the copper hydroxide doesn't have a charge on it. So again, both sides there is a charge of 0. Okay, are there any spectator ions? The sodium and nitrate ions are exactly the same on both sides of the reaction. So 2 hydroxide ions and a copper ion is going to form copper 2 hydroxide precipitate. And right there is an example of another net ionic precipitation reaction, where the ions come together to make the insoluble precipitate. Doesn't matter if the copper or hydroxide on the left side of the reaction, if copper has to be first or second, that does not make a bit of difference at all. Just as long as when you are done, the reaction is balanced in 2 things. When you have net ionic equations, they have to be balanced in 2 things. It has to, first of all, be balanced in atoms. Okay, so there's 2 oxygens on the left. There are 2 on the right. There are 2 hydrogens on the left. There are 2 on the right. There's a copper on both sides. The atoms are balanced. The second new thing now that we have to be careful of is the reaction balanced in charge. There is 2 -1s and a +2. That adds up to 0 on the left side of the reaction, and there's 0 on the right side. So the charge is balanced on both sides of the reaction as well. Okay, so that's how we do precipitation reactions. Starting from the balanced molecular equation, identifying states of matter, dissociating the aqueous substances, crossing off spectator ions, and whatever we're left with is a net ionic equation. I strongly urge, I'm going to give you some practice homeworks in Canvas after watching this video. Please, please, please make sure you do these homework problems and get practice doing them. If you do that, this should not, again, be a very difficult concept, but one that you just need to practice to gain the mastery in. One little note. Sometimes here's an example of a net ionic equation, and the reason why I'm showing you this, okay? If I were to put zinc metal into an acid, what would happen is I would form the products of zinc ions. The acid would dissolve the zinc metal, and I would form hydrogen gas. This is an example of a net ionic equation. The reason why I'm showing these very quickly is I don't want you to think that both sides of the arrow have to always add or be 0. In this reaction, the zinc has no charge on it. As a metal, it is a neutral atom, but there's 2 hydrogen ions that each one is +1. So that adds up to a total of +2 on the left side. On the right side, the hydrogen is neutral, but the zinc is +2. So on this reaction, you have both +2 on the left and +2 on the right. That is still balanced. The charge is the same on both sides of the reaction, +2 and +2. So don't think that they always have to add up to 0 on both the left side and the right side. What has to be balanced is the same charge on the left is the same on the right. All right, a couple of little things to kind of finish up and wrap up this lecture. I know I'm already long, but it's very tough in AP not to keep them under 20 minutes, so I'll try to be brief here. When sodium chloride is placed into water, solid sodium chloride is readily soluble in water. You know that sodium chloride is table salt. When you put it in water, it dissolves, and the sodium ions and the chloride ions dissociate into solution. Now, since they're floating around in solution, what prevents the positive and the negative ions from recombining? This process is called solvation. If you remember, water, if you were to draw a geometric shape of water, water has got a bent configuration. It's bent like a V. Water is a polar molecule. It's polar, which means part of the water has got a negative pole and part of it has a positive pole. Do you remember which one is which? Oxygen is more electronegative than hydrogen. It's the element closest to fluorine. Fluorine is the most electronegative atom. And because of that, the oxygen is the negative end of the molecule. Directly opposite it by the hydrogens is the positive end. Because water is polar, it has both a positive and negative end to the molecule. And that is very much strongly attracted to the ions in sodium chloride. So, what keeps the sodium ions and the chloride ions from recombining? Well, this sodium positive 1 ion in solution as a particle, what part of water is going to be attracted to the positive sodium ions? The oxygen or the hydrogen? Unlike charges attract. So the oxygen part of the water is going to attract, and that water, multiple water molecules are going to surround this ion. And this process of the water molecules surrounding the ion, this process is called solvation. And because the water molecules are circling the sodium ions, that prohibits or prevents the sodium and chloride ions from getting together. The more attracted the water molecules are to these ions, the more soluble the ionic compound is in water. Okay, if it's not as soluble, it's because the water is not as strongly attracted to it, and therefore not as much of it will dissolve. Things that are readily soluble, water has a great affinity or attraction towards it. If you're asked to draw a picture of solvation around the chlorine ions, it'd be flip-flopped. Though the hydrogens would be closer to it. Now what I'm doing here is showing you a different way in the national exam that they tend to show it. They tend to show water almost as a Mickey Mouse because hydrogen atoms are so much smaller than oxygen atoms. So when you draw it, you might see water represented as a particular representation as literally as two small circles and a bigger circle, where the two hydrogens are bent. And still we see that bent, that V shape in the structure, but the positive end of the molecule is by the hydrogens and the negative end is by the oxygens. And so you could see on the national exam a picture showing it like this, where the hydrogens, which is the positive end of water, is much more attracted to the chloride ions than the oxygen is. And now because those water molecules are getting between the ions, they prevent them from recombining, and therefore the sodium chloride stays in solution form. It's a soluble in it. And these negative ions in this solution now causes water to have an electrical current, to be electrolytic, and that's why we call these substances electrolytes. All right, last thing. It says equal molar quantities of sodium iodide and barium nitrate are mixed in a beaker. All right, so I've got sodium iodide, and they said solutions. So immediately, because they said solutions, oh, they didn't say solutions, my fault. On the quiz or test, I would say that they're solutions. Barium nitrate is BaNO3. Any element in group 2 has got a +2 charge. Barium nitrate's always -1. These are soluble because sodium is a group 1. Nitrate is always soluble. When I mix them around, I'm going to form barium iodide. Barium iodide is an insoluble precipitate, and sodium nitrate is readily soluble, aqueous. We need 2 nitrates, so we need 2 sodium nitrates, we need 2 sodiums, need 2 over here, 2 iodides, 2 iodides. There's the balance reaction. It says once precipitation is complete, please draw a picture at the molecular level of all the substances where each is found in the beaker. So let's say I got a beaker, and here's the water level. When I mix these two chemicals together, you are going to see solid on the bottom. And if I were to label that solid, what would that solid be labeled as? Barium iodide. Okay? In solution then, you'll notice that since the barium and iodide is precipitated, you'll notice that the sodium nitrate is still aqueous. And therefore, we are still going to see sodium ions and nitrate ions in the solution. Now the key word here is at the very beginning. It says equimolar. Equimolar means I'm going to add equal quantities of sodium iodide and barium nitrate. So I'm going to have equal quantities of these guys. So I'm going to have 1 sodium to 1 iodide to 1 barium. But the nitrate's unique in the fact that because it's an equal mole quantity, I'm going to have twice as many nitrates into the solution. Okay? So if I'm mixing these equal molar substances together, you'll notice that there's going to be twice as many nitrate ions because every barium nitrate provides 2 nitrates for every barium. Now the barium, sodium, and iodine would be in the same ratio. Okay? They'd be 1 to 1 to 1. Now if I look at the chemical reaction tells me that when I mix these ions together, that it's going to react in a ratio of 2 sodium iodides to every barium nitrate. So I need twice as many sodium iodides for every barium nitrate in order to be reacted. It's a ratio of 2 to 1. Because they're equimolar, that tells me that because the barium requires twice as many sodium ions, twice as many iodide ions, the barium ions, okay, will not be fully precipitated because every barium ion requires at least twice 2 iodide ions. Because of that, because it's taking 2 sodium iodides to every barium nitrate, there will be still some barium left in the solution. And not all of it will be precipitated out because we are not adding equimolar concentrations. Because we're adding equimolar, we're not mixing twice as many moles of sodium iodide to barium nitrate. Because I'm consuming the 2 to 1 ratio, that means that the iodide ions will no longer be present in the solution. All of them will be precipitated out in the form of barium iodide. So because of this 2 to 1 ratio, and because I mixed 1 to 1, that tells me that the sodium iodide solution is going to end up being the limiting reactant. And specifically not the sodium, but the iodide ions, because it's the iodide ions that are precipitating out of the solution. So by identifying the iodide as being the limiting reactant, there will be no iodide ions in the solution. There will be still barium in the solution, okay? And right now, if you were to draw this picture, you'll notice that if I add up the sum of all the charges of the substances, you'll notice that it's -1, plus 2, plus 1. You'll notice that it does not balance in charge. And therefore, I've got +3 and -2. So I need another nitrate ion present in order for this reaction to be fully balanced. Okay? So because I added equimolar barium nitrate to sodium iodide, and it requires twice as many sodium nitrate ions per every barium nitrate ion, I know that the sodium iodide is the limiting reactant. And because the iodide is being precipitated out, it will no longer be in solution. It's all going to be in precipitate form. The barium is still, a small amount of barium is still in the solution because of the fact that it was the excess reactant, and therefore some of it will stay in solution form, some will be pulled out as the precipitate. And lastly, when you're done, you have to make sure that the overall charge in the solution stays neutral because of the overall reactions be balanced both in charge and in atoms. This is a very difficult concept with pictorial examples, and I promise to give you much more practice doing this, but I did want to introduce it to you, and again, I apologize for the length of this video, but if you have to pause it from time to time and come back to later to finish off, please do. But these are some very large concepts in this first unit, and I'll be glad to talk more about these as we continue to go throughout this unit in solution chemistry. Now, the homework primarily is going to be focusing on doing net ionic equations for precipitation reactions. So like we did at the top where we do the reactions. Please try those homework problems. If you have any questions, please ask me. Again, thanks for listening.